Hello, in this talk we will discuss about the different ways by which corrosion, different types of corrosion can be prevented. So, if you talk about particularly in case of the aqueous corrosion, how should we take important measures so that the corrosion kinetics can be reduced and it can be prevented to a large extent. So, this is the summary slide which shows the different ways by which corrosion may be prevented. Especially most of the ways are applicable for combating the aqueous corrosion, and some of the techniques are applicable for the combating the liquid metal corrosion. Some of the techniques are for high temperature oxidation. So, if you talk about the aqueous corrosion, it is basically these are basically aqueous corrosion based problem can be circumvented or maybe can be reduced by a choice of the proper materials, by the application of cathodic protection, by the application of anodic protection, by the application of the inhibitors where you change the environment, by proper designing of the component, and by application of surface modification and coating techniques. Now, if you talk about high temperature oxidation based corrosion, high temperature oxidation based corrosion can be avoided or can be minimized by proper choice of material in that specific environment. It can be minimized by application of surface modification, particularly surface alloying. It can also be minimized by the application of coating. Now, if you talk about liquid metal corrosion can be avoided by proper selection of the materials combination. You can also get rid of the liquid metal based corrosion by the application of coating. So, you have to understand that which kind of corrosion your component is facing in that particular environment. So, accordingly you choose the material and just go on taking different precautionary measures so that corrosion can be minimized. So, now this is the summary sheet. Our basic goal is to protect the material from corrosion and avoid the localized corrosion. So, whenever it is possible you choose that. These are typical thumb rules which must be followed for minimizing the corrosion kinetics in actual component. Like whenever it is possible you choose the noble materials like the material noble, or otherwise in that material some stable film forms, passive film forms which protects the underlying substrate. Then avoid electrical or physical contact between the metals to avoid to get rid of the problem of the galvanic corrosion. If dissimilar metals are in contact, make sure that the anodic metal has a larger area to volume ratio, that is typical design criteria. You have to follow the proper thumb rule for designing of the dissimilar components. Particularly in case of microstructure level galvanic couple, try to use a coarse microstructure to reduce number of galvanic cells, coarse microstructure, or in other word I must say try to use a homogeneous component with homogeneous microstructure, so that there is no chance of or possibility of formation of microgalvanic cell. Even if it is formed, it is basically uniform all throughout. Modify the base alloy by alloying, then protect the surface by various means like painting or use some alloying operation or use some coating. So, modify the fluid by the application of different inhibitors and cathodic protection or anodic protection. Cathodic protection uses sacrificial anode or maybe an external DC source in connection with the inert or expanded cable. So, these are the different precautionary measures you must take in order to get rid of the aqueous corrosion problem. If you talk about the high temperature oxidation problem, as I mentioned you that you have to apply certain alloying element on the surface by the process of surface alloying, either by pack cementation based surface alloying process or by the application of laser surface alloying, so that whatever surface you are modifying, that is basically protective in that particular environment. Protective in that environment means that whatever film is formed out of that alloying element, that film is highly stable in terms of its strength, in terms of its diffusivity through the oxide is very low, in terms of ionic conductivity. So, these film which are forming on the surface is highly protective in nature. Whenever it is the case for liquid metal corrosion, then in that case you basically you can apply that coating which can either you change the material or use proper material in that proper liquid corrosion environment, liquid metal environment, or apply a very thin layer of coating which is actually which does not protect the which does not participate in the liquid metal embrittlement process, and by that process it modifies the underlying substrate. It basically protects the underlying substrate. So, these are the guidelines which you must follow for preventing or for minimizing the probability of different types of corrosion. Now, if you talk about proper selection of materials, especially the aqueous corrosion based problem, you will find that different materials behave differently, and these charts gives you guidelines about which material which behave or which material will not corrode in particular environment, particularly when this is the case for general corrosion. Because for stress corrosion cracking we saw separate list, for liquid metal embrittlement we saw separate list. So, particularly for general corrosion based problem, steel is highly safe to carry concentrated sulfuric acid. Stainless steel is highly safe to carry the nitric acid in the nitric acid solution. Nickel and its alloy is very safe in caustic solution. Monel is very safe in hydrochloric acid solution. Hest alloy is safe in hot hydrochloric acid. Lead is safe in dilute sulfuric acid. Aluminium is safe in non-staining atmospheric exposure. Tin is safe in distilled water. Titanium is safe in hot strong oxidizing solution. Tantalum is safe in all environments. So, this gives you a proper guideline of the choice of material, particularly the corrosion, particularly for that case when corrosion is basically general corrosion based problem. But if it is stress corrosion based problem, then you have to follow the chart for the stress corrosion. If it is liquid metal embrittlement, you have to follow the chart for liquid metal embrittlement. Whenever it is high temperature oxidation, you have to follow Ingham diagram, or also you have to follow the typical alloy, or you have to choose the different alloy which actually does not undergo corrosion in that particular environment by forming a very thin protective oxide film. So, proper choice of material is very important. Usually sometimes you do alloying also to reduce the corrosion tendency, like chromium is alloyed usually because chromium saves the material from in neutral and acidic environment. Molybdenum saves in chloride and sulfuric acid environment. Nickel resists stress corrosion cracking at higher level. Manganese reduces the pitting corrosion resistance. Molybdenum reduces the pitting corrosion, manganese reduces the pitting corrosion resistance, molybdenum enhances the pitting corrosion resistance property, carbon is responsible for intergranular corrosion, stress corrosion cracking. So, nitrogen improves the pitting. So, these are the few guidelines where the role of alloying element in controlling the different corrosion behavior or corrosion property must be known to you prior to designing the alloy for specific application. Now, second technique which I will discuss is the cathodic protection system, which is mostly applied or can be applied widely for protection of the surface against the aqueous corrosion based problem. So, cathodic protection is nothing but a kind of technique where you make the component of your choice as cathode. So, this can be done by two ways. First way is by just attaching it or connecting it with another material which is anodic to that metal to a large extent. So, when you connect an anode with your component, then what happens is that corrosion process is surrounded by the or corrosion basically proceeds in the anode. Anode is mainly subjected to the corrosion. So, whenever the anode is subjected to corrosion, naturally by corrosion there is evolution of lot of electron, and that electron whenever is evolved, naturally your cathode is highly protected. So, your metal is highly protected, otherwise also it is acting as cathode. So, there is no corrosion at all. So, this is very important way of protecting the metal from any kind of corrosion, say maybe any kind of aqueous corrosion I must say. It may be general corrosion, it may be pitting corrosion, it may be stress corrosion cracking, it may be hydrogen embrittlement. So, any kind of corrosion can be taken care of by typical cathodic protection process. By this cathodic protection, you basically make your component as cathode and by this process naturally indirectly you minimize the corrosion, you can get rid of the problem of the corrosion to a large extent. So, this is the typical cathodic protection which is observed in pipeline. For example, whenever it is not protected you see lot of rust on the component, but whenever it is protected by typical exposing, by connecting it to typical anodes, you will find that this is highly lustrous surface and it is protected. So, this is basically a kind of galvanized steel. So, galvanized steel whenever you use naturally it protects the surface by two ways. One way is by typical barrier coating, another way is by sacrificial coating where it protects the underlying substrate by cathodic protection. Similarly, this is the case for bridge. Bridges you are usually connected to magnesium pieces like anodes at regular interval by typical wear. So, whenever the magnesium anodes are there all throughout the bridges at regular interval, what happens is that corrosion happens in magnesium in contrast to that of your steel. So, your steel structure is protected. So, what you have to do is that at regular interval you have to inspect the corrosion rate of the corroded species, corroded magnesium, so that you can say that whether corrosion whether your steel can be protected further, and or otherwise you can also estimate the amount of the or volume of the magnesium required for protecting the component for several years, or accordingly you can also calculate the lifetime of the component. So, this particular means is a very widely used means for protecting the large structure against the corrosion process. But one of the important problem associated with that cathodic protection is the stray currents which happens in the electrolyte from external sources. So, whenever you use cathodic protection, particularly below that of earth, there you will find that because of the cathodic protection or because of cathodic protection, especially when you just do connect it with the DC sources, you will find that if there is any other corroding species they gets corrodes away, so that gets further trouble. So, you have to be very much careful in building the structure next to the cathodically protected structure, so that it cannot corrode. So, another way of protecting the surface is by anodic protection. This is completely the reverse case. Instead of connecting the surface with more anodic material or maybe passing the electrical current, so that your components act as cathode, you cathode, you use the reverse way, that is you try to use your component as anode by basically connecting it with the electrical sources, power sources. So, when it is acting as anode, naturally you will see that the corrosion rate of your component increases to a large extent. So, when it increases to a large extent, naturally there is a formation of the oxide scale on the surface. So, when there is formation of oxide scale on the surface, you will find that they are passivated, you say it as passivated, and that passive film actually helps in reducing the corrosion rate further. So, this is the case for the self passivation by the anodic current. So, you will find that the component gets protected. So, this particular anodic protection is applied only for those particular component which is very prone to corrode actually, and where there is formation of passive film, and that passive film is highly protective in nature. So, if you compare the cathodic protection and that of anodic protection, you can understand that cathodic protection is more versatile, can be applied for any materials and can be applied for getting rid of any kind of aqueous corrosion problem. But anodic protection can only be applied which undergoes active passive transformation, active passive behavior, and more aggressive corrodants can be handled. So, operating cost of cathodic and anodic, you will find that operating costs are lower in anodic protection, although installation cost is higher, and cathodic protection is having always lower cost, and cathodic protection is a standard system and well established, and feasibility can be naturally anodic protection you have to know actually whether at all anodic protection can be applied for this material. So, you can say that cathodic protection is highly versatile and can be widely used for all kind of materials. You can also change the environment. So, if you talk about changing the environment, can be done by just by getting rid of the external parameters or reducing the external parameters which aggravates the corrosion rate, like velocity aggravates the corrosion rate. So, if you decrease the velocity, your corrosion rate will be reduced. If you reduce the temperature, corrosion rate will be reduced, because even though corrosion happens in aqueous media, but kinetics, it is again thermally activated process. So, as you go on increasing temperature, rate of corrosion increases. You can also remove oxygen or oxidizer, you can also change the concentration. So, by these all ways you can always alter the environment. So, if you talk about altering the environment, as I mentioned, you can reduce the temperature, you can reduce the velocity, but sometimes these are not under your hand. So, you cannot really play with them, because those are the natural things and where you have to use your component. So, in that case you can apply inhibitors to reduce the aggressiveness of the media, aggressiveness of the particular environment. So, if you talk about inhibitors, they are again added when added in the solution or in the environment. They either reduces the aggressiveness of the environment, or they take away some species which cause corrosion, or otherwise it can also get absorbed over the surface, and by that process protects the surface. So, there are different types of inhibitors available which are applied to protect the surface from corrosion purpose. They are adsorption type inhibitors, hydrogen evolution poisons, and then scavengers. So, adsorption type inhibitors means oxide that it basically get absorbed over the surface like organic mines. So, when you just sprinkle it in the environment, it gets absorbed over the surface, and by that process it acts as a barrier. The surface is no more in contact with the solution. When it is hydrogen evolution poisons like arsenic and antimony ions, it basically takes away, it basically it is poisons, basically it basically reduces the tendency of hydrogen evolution, and by that process it reduces the tendency of those corrosion, particularly hydrogen embrittlement, stress corrosion cracking problem to a large extent. Scavengers again takes away oxygen from the system like sodium sulphite and hydrogen. They basically takes away oxygen from the system, and by that process it reduces the aggressiveness of the environment. So, corrosion inhibitors is very important. So, it is nothing but chemicals which are added in small quantities to the corroding media in order to reduce the corrosion rate. They reduce the corrosion by forming a protective film either at the cathode or anode. There are two types of inhibitors like cathodic inhibitor or anodic inhibitors, or also mixed inhibitors. So, anodic inhibitors actually they are basically like chromate, phosphate, the tungstates, they are anodic inhibitors. They react with the metal surface and then form protective film or barrier that are preventing further corrosion. So, anodic inhibitors are very interesting. They basically helps in the process of formation of thin protective film, as you see in case of that typical anodic process of the anodic protection system. So, name is more or less similar. In case of anodic protection, you basically allow the component to act as anode, so that there is formation of a thin continuous passive film. So, anodic inhibitors also you add in that system in such a fashion that they react with the metal surface and form the metal compound, so that it is preventing further corrosion. And cathodic inhibitors are the inhibitors, there basically their reaction takes place with either evolution of hydrogen or absorption of oxygen, depending on the nature of the corroding media. So, they make your component basically cathode, so that it does not react with anymore, because whatever hydrogen or whatever oxygen you are generating, they get consumed by the inhibitors. So, there is always hydrogen evolved in the media. So, evolution of hydrogen can be prevented by slowing down the diffusion of hydrogen ion to the cathode or by decreasing the hydrogen over voltage. Diffuse of hydrogen ion can be prevented by adding organic inhibitors such as amines, urea, thiourea. They are absorbed at the surface as film. Arsenic oxide or antimony oxide is added to increase the hydrogen over voltage. These oxides form adherent film of metal arsenic or antimony at the cathodic sites. So, absorption of oxygen can be done by typical sodium sulphate, so hydrazine. These kind of agents or chemical compound, they basically consumes oxygen from the system. So, when they consume oxygen from the system, so no more free oxygen is available, as a result of which your component get protected. So, finally, the corrosion can be prevented by the application of surface engineering techniques. So, if you think about different surface engineering techniques that, or maybe different surface parameters which control the corrosion kinetics, they may be categorized into different sectors. Like first important parameter which controls the corrosion kinetics is surface energy. So, if you just expose the surface with higher energy, it will be more prone to corrosion. On the other hand, if you expose the surface with lower energy, it will be less prone to corrosion. Surface roughness plays very important role. Rougher the surface, more will be the exposed surface area, as a result of which more corrosion will be there. Particularly when surface is very rough, you will find that there will be chance of more pit formation also at the surface rough region, because they may act as a site for pit initiation, they may act as site for the stress corrosion cracking initiation. So, surface roughness plays a very important role in controlling the many of the initiation mechanism, in addition to increasing the overall surface area of the component. Microstructure and composition, they are very important, because ultimately it is the surface microstructure and composition which controls everything. So, if it is uniform microstructure and composition, then the corrosion mode will be uniform. If it is non-uniform, there will be galvanic corrosion. If it is around grain boundary several precipitates, then there will be intergranular corrosion. There may be some stress corrosion cracking problem. So, surface microstructure and composition is very important, which controls everything. Surface hardness is also important, because surface hardness influences the erosion corrosion behavior. It can also influence the stress corrosion behavior to a large extent. And finally, fracture toughness. Fracture toughness is another parameter which controls many corrosion problem, like stress corrosion cracking problem is controlled by surface toughness. Then again, if you talk about cavitation corrosion is controlled by surface toughness. So, these are the parameters which control the aqueous corrosion property of the component. If you talk about high temperature oxidation, then high temperature oxidation is predominantly controlled by surface energy, then surface microstructure and composition, and surface toughness. If you talk about liquid metal corrosion, it is controlled by surface microstructure and composition, and then surface toughness. So, like that, you have to know what are the parameters which control the different corrosion properties, and also you have to know the what exact values you are looking for improving the corrosion resistance to this particular level, what microstructure and composition I am looking for. So, like that, you have to design the surface very nicely very in advance, so that you get the desired property. Then you can go on modifying further by different other routes. Now, coming to the different techniques which are available for the corrosion protection, they may be categorized under two types. One is surface modification and coating, second one is coating. So, surface engineering techniques are nothing but tools which are applied to change the surface or to tailor the surface. So, they may be categorized into two types, one is surface modification, another one is surface coating. Surface modification deals with a series of techniques where you modify the existing surface, so that it is part of the surface, part of the component. On the other hand, coating deals with a series of technique where you apply completely another layer on the surface. So, there is a sharp interface or diffused interface between the coated layer and the component. So, if you talk about different surface modification techniques may be applied for mitigation of the corrosion, they are of three types. One is short pinning, second one is surface melting, third one is surface alloying. So, short pinning can be applied for introduction of the stress on the in the component. So, short pinning is a very important category of surface modification technique, and usually it can also be applied for modification of the surface in case of stress corrosion cracking, in case of corrosion fatigue. It can also be applied for mitigation of the corrosion, especially when the fretting corrosion is there. So, these all kind of corrosion where stress is responsible, there the short pinning can be applied. Similarly, another type of surface modification technique is surface melting. So, surface melting especially can be applied for homogenization of the microstructure, especially when you melt with the help of high energy laser or electron beam. So, when you go on melting the surface using high energy laser or electron beam, it basically refines and homogenizes the microstructure. So, by that process it can control some of the corrosion problem like intergranular corrosion, it can control the galvanic corrosion, it can also control the stress corrosion cracking to a little extent. Finally, surface alloying is another surface modification technique which basically enriches the surface with other alloying element and which prevents the corrosion to a large extent. So, surface alloying may be applied for prevention of the corrosion, particularly when it is of for example, galvanic corrosion, when if it is of high temperature oxidation, if it is of general corrosion, surface alloying may be applied. So, these are three surface modification techniques which might be applied to combat the corrosion problem. If you talk about coating techniques which may be applied, they are painting. First of all, painting is a versatile technique which is widely applied for protection against corrosion of any kind of material when exposed to the environment. So, it acts as a barrier layer and saves the surface from corrosion. Chemical, electrochemical conversion coatings can be applied for protection against corrosion. Electrolyte deposition can be applied. Hot dipping can be applied for protection against oxidation, because hot dipping basically applies a very thin layer of can be used for application of zinc coating or aluminum coating. So, by that process it saves the surface from oxidation. Weld overlaying is another technique which can be applied for development of a thick hard coating, it may be called as hard facing. So, weld overlaying may be applied for mitigation of the corrosion like cavitation corrosion, for the mitigation of pitting corrosion. These all corrosion can be mitigated by the process of weld overlaying. So, these are the different techniques which are applied, and then we will be discussing about these few techniques in the next classes, and have already been discussed some of the techniques. So, thank you very much.